Okay, good day, class. We'll continue with our discussion this course, Electromagnetism. But before that, we'll have a short review on the vector analysis, specifically on the position, displacement, and the separation vectors. So let me just how do I make this full screen? Oops. Okay, that's it. So first thing, we go back to the our discussion on position, displacement, and separation vectors. So the location of a point in 3 dimensions can be described by listing its Cartesian coordinates, so x, y, z. So position niya in terms of x, so y, and z could be 1, 2, 3, or could be sa 3, 2, -1. So the vector to that point from the origin is called the position vector. So always na siya from the origin to the position or to the point in question. So this is the position vector r, and r hat is your unit vector, the direction of the direction of the vector r, which is along in this direction. Okay, so we have this convention nga ato ang gamiton for this course, electromagnetism. For the source point, it is denoted as r prime. So from the origin up to the point in question, that's r prime. And we also have the field point. So ang source point could be the source of your electric field. So it could be a positively charged particle or a negatively charged particle. Then your field point is it could be anywhere. So, okay, ang field point is, this is, you test what is the strength of the field produced by the source point. So this is what we call the field point, and it is denoted by vector r. Okay, and the distance between the source point and the field point. So most of the time in our course, in this course, we will be employing or utilizing the script r, or the separation distance between the source point and the field point, and we don't have to worry about the origin anymore. So it's just the distance between these 2 points in question. So the position vector r is given by equation 1. It is expressed in this form. So you have the magnitude x and the direction x hat plus y hat plus z hat. Its magnitude is given by equation 2. So you get the square root of x squared plus y squared plus z squared. Okay, and it is the distance from the origin. Okay, ganun siya. And the unit vector r hat is given by this. So it's just the ratio between the position vector r and the magnitude r. And the position vector r is given by this form in the numerator, while the magnitude r is given by the expression in the denominator. So we have equation 3. So this is a unit vector, this r hat, pointing radially outward. So outward in all direction, outward. And the infinitesimal displacement vector form infinitesimal displacement vector from xyz to this much x plus dx plus y plus dy, and then z plus dz is given by equation 4. Okay, so it's just a small change of displacement. So it's infinitesimal displacement vector, small change with respect to x, the y, and the z. So you have small change in x, small change in y, and then small change in z. So in electrodynamics, one frequently encounters problems involving 2 points, typically a source point, as I've said at the beginning, r prime, and a field point r, and you want to calculate the electric field. So we'll adopt some shorthand notation for the separation variable from the source point to the field point, and we call that a script r. Okay. So actually this is kanisha script r. This is sa kaning latex man good is I wasn't able to modify it in such a way that this should be a bold face r. So since naglisod man ko og pa boldface ani niya, siguro sa missing packages sa kaning latte, I just put an arrow sa taas. Okay, it signifies a vector. While this one, wala siya arrow sa taas, but it is a boldface notation, so this is a vector. So post na sila mga vector, okay? So this is a vector script R for the separation variable, and this is equivalent to by just saying the difference between the field point and the source point. Okay, so this is the source point, the R prime, and the vector R is the field point, and its magnitude is given by equation 6. So you have this, and a unit vector in the direction from R prime to R is given by equation 7. So the unit vector is given by the ratio of the separation vector R and then the magnitude of the separation vector. So we have this form. So in Cartesian coordinates, the separation vector or variable is expressed in equation 8. Diba? So it's kaganina, instead na x lang, instead na y, instead na z, we have now the difference between the field point and the source point. So the field point and the source point. And its magnitude is given by this, the same formula na siya. And the unit vector separation, or the unit vector of the separation variable R is given, script R is given by equation 10. Okay, now let's move on to the one of the new concepts in this course, aside sa katong sa position, separation vector, and displacement, we have the term gradient. So gradient is actually a generalization of the notion of a derivative to functions like t, so which depends not on one variable but on three variables. So a theorem on partial derivatives states that we have this equation 11. So this is just a derivative, right? And we can express it in terms of partial derivatives by having this by having this form in the right hand side of the equation. Okay, we have partial of t with respect to x, and we have dx, partial of t with the partial of y times dy, and we have partial of t with respect to z, then we have dz. So this tells us how t changes, let's say temperature. So how t changes when we alter all three variables by the infinitesimal change dx, dy, dz. Okay? So it tells you how much t changes if you change the displacement by a small amount. You have dx, dy, and dz. So dt is reminiscent of a dot product, so we can somehow manipulate this equation 11 in the right hand side of the equation to look like this. Okay, so this right hand side of this equation 11 is equal to the right hand side of this equation in 12. Okay, so it's just a dot product. Take a look. So partial of t with respect to x, then we have a x hat, is a vector, unit vector. Partial of t with respect to y, and so on. Dot with, now this is a familiar form. This is the infinitesimal displacement, right? Or the displacement vector. We have dl, and we can denote this entity here as gradient of t. Okay, or we call this as nabla. This is nabla in Greek letters as symbol. So this is termed as gradient of t dot with the small change in the displacement, or displacement vector. So as I've said, t is the gradient, delta t, nabla t is the gradient of t. So gradient of t is a vector quantity. Okay, why? Because the product of two vectors, this is a vector, this is a vector entity also, then that product of that should be a scalar. After all, derivative of t is just a scalar quantity. It's just a number. Okay. So gradient of t is a vector quantity with three components, and it is generalized derivative we have been looking for. So, di ba, in your previous math, you've discussed ordinary derivatives. You have derivative with respect to x, derivative with just respect to y only, or derivative of anything with respect to z only. Now in this case, it's a derivative with a derivative of something in terms of three components, the x, y, and the z. So note that since it is a dot product, so we have the magnitude of these two times cosine theta, right? Because it's just by virtue or the definition of a dot product. So gradient of t dot with dl is just this. The magnitude of gradient of t and the magnitude of dl times the angle between them. So that's the angle between them. So thus, the gradient, this one, points in the direction of maximum increase of the function t. Moreover, the magnitude of gradient of t gives the slope along this maximal direction. So, kani siya. So, we'll be looking at one example to just be able to demonstrate how do we get gradient of anything or something. Like in this case, how do we find the gradient of this magnitude r? Okay, so we are given with this one. R equals the square root of x squared plus y squared plus z squared. So we are asked to find the magnitude. We are asked to find the gradient of this r. That is the magnitude of position. This is the magnitude of the position vector r. So we can use the formula for finding the gradient of this. So the formula is this one. Okay. So it's just this one. Okay, it's just taking the derivative of. Okay, this is actually a vector entity. So taking the derivative of r with respect to x. We have also for the y. Okay, then what are we going to do is to take the derivative of r with respect to x. So we know how to take the derivative of this one. We just have to make use of our prior knowledge on taking the derivative of such. So nauna mo na siya, diba? So we have, this is, the whole thing is equivalent to this one, to the 1/2. So the idea is you bring this 1/2, this exponent down. So we have 1/2, and then copy everything what's inside, and then the exponent would be deducted by 1. So we have 1/2 minus 1, and that would give you negative 1/2, right? And then after that, you take the derivative of what's inside with respect to x. So this is just a constant entity because this, we can take the derivative of this whole thing with just respect to x. So everything else will be 0, while we take the derivative of this, which is 2x. So that's 2x, okay? And then the same thing happens when you take the derivative of this r with respect to y and also with respect to z, okay? You take the same process. So that would give us 1/2 x squared plus y squared plus z squared to the negative 1/2. Then taking the derivative of the inside, it's equal to 2y. Okay. Oh, I forgot. There should be a since taking the gradient of magnitude is the result is actually a vector entity. So we have x hat. So we have y hat plus 1/2. Okay. X squared plus y squared plus z squared negative 1/2. Then this is z hat. Okay, we have this one. So simplifying this whole thing, we get 2x. Okay, we get 2x and over square root of x squared plus y squared plus z squared. Then we have the unit vector x hat plus 1/2. Then we have now 2y. Okay, sorry, nakita. So we have x squared plus y squared plus z squared. Then y hat plus 1/2. Oh, okay na din. Times we have 2z over x squared plus y squared plus z squared, and then z hat. Okay, then we can still further simplify this equation here. So this one cancel na ang 2, cancel ang 2. So we are left with x hat. Then common sa tulo is this entity here, square root of x squared plus y squared plus z squared. So kana lang. So we have y hat plus z hat all over this whole thing. We have x squared plus y squared plus z squared. Now we know from our previous lesson that this entity here is just your vector r, and then the denominator is just your definition of the magnitude r. Okay, but this whole thing, can you see, this is your unit vector r, or r hat. Okay, so it actually makes sense, because if you want to take the gradient, the direction or the gradient of this magnitude r, you get the direction of its maximum change or maximal change kung asa ang ihang direction, which is radially outward. Okay, this is r hat. Now another important quantity or entity in electromagnetism is the idea of divergence. So sorry, nasayop na siya. Okay. So a point of divergence is a source or a faucet. A point of negative divergence is a sink or drain. So when you say divergence, like how spread out it is, right? So if we have two kinds of divergence. It's either a sink or a drain. It's either a drain or a faucet. So a faucet is, if you've seen a faucet, it spurts out water. So that's a positive divergence. Then if you have a drain sa inyong below sa inyong faucet, sa inyong sink, right? So it has a drain there. So that's what we call a negative divergence. In mathematical mathematical terms. So this is the one of the examples of having a positive divergence or not. But for letter A, it has a very large positive divergence because it's spread out away from the source. So it's like a faucet. For letter B, you might guess, what's the value of divergence? Actually, for letter B, it has no divergence. So the value is 0. So wala siya, it doesn't diverge. Take a look at it has all arrows pointing upward with equal length. So it doesn't diverge. It just stays the same, constant siya. However, for letter C, so the arrow keeps on changing from gamay siya tapos nagkadako. So it has some value of a divergence. So it has a positive value na divergence. So from the definition of nabla, so we construct the divergence given by equation 16. So we have del dot v. Okay, so this is del dot v. Del is defined by this form kaganina sa gradient. Mamo na siya atong gigamit nga expression. So you have partial of x, partial of y, partial of z. Sorry about that. Okay. And then dot with any vector. See, you have vx, vy, vz. This could be of, let's say, any siyang examples of vector. It could be wind, it could be electric field, magnetic field. Okay. So if you dot that one, notice or recall that if you have a dot product of two vectors, the result is always a scalar quantity. Okay, so the divergence, the output of divergence of something is always a scalar quantity. So it's just a number. So observe that the divergence of a vector function is scalar, and you cannot have the divergence of a scalar because it doesn't mean anything. Di ka pwede makamultiply og vector, di ka pwede maka-dot product of a vector and a scalar, so it's meaningless. So the divergence is a measure of how much the vector spreads out from the point in question. Kung unsa siya ka-diverge, that would tell you how much its value depending on kung unsa yung result sa itong calculation. Okay, so let's take a look at this example in calculating the divergence of any vector entity. So let's say we have three vectors here. We have figure A, figure B, and figure C. Now this is the one that I've showed you a while ago. So we have this vector. It diverges into this in all direction, and we have also this vector and vector C. Now suppose that these figures that we have here is represented by this equation. So suppose the function in figures A to C are of this form. So for VA we have this equation. This is just your position vector, right? And for the second figure, the function is given by this. It's just z hat. And for figure C, we have this function here. Now calculate the divergences. So divergences. Okay. So how do we calculate the divergence of each for VA, VB, and VC? So let's solve. So for letter A, okay, so the formula for divergence is just this, del dot VA, and our form for the divergence is just so we have x hat partial x plus y hat partial y plus z hat partial z, and then dot with our vector equation, this one. So we have x hat. Okay, now we take the dot product of this. Now we already know how to take the dot product of two vectors. You multiply the same or you multiply like terms, right? So we have this one multiplied by this. So we have partial of x, then we have x, well, x hat dot with x hat using the right hand rule. This is just equal to 1. So we have this, because after all the dot product of two vectors is just a scalar quantity. So we have this partial y plus partial z. So this is just 1 plus 1 plus 1, so this is just 3. So the value of the divergence of this vector having this form is equal to 3. Okay, now how about for the vector function in B? So the same process. So you have del dot VB. So you have x hat partial x So for VB, it's just the Z hat. Okay. So since only the Z hat is present, no X hat and the Y hat component, so if you multiply that one, it's just 0. You're only left with this, right? So partial of Z, so this becomes partial of Z. So actually 1 lang na siya because Z hat times Z hat, Z hat dot Z hat is just 1. So partial of 1 with respect to Z, this will just give you 0, right? So it makes sense because after all, I've said in my PowerPoint presentation a while ago that this vector, assuming klaro akong pagka-drawing, this is of equal length and pointing in the same direction, this has no divergence actually. So as we can see in our calculation, the divergence is just 0. Okay, for letter C in vector V sub C, so the same process. Z hat. So only the Z hat term is present. So we can ignore the X and the Y because these are just 0. So we have partial of Z with respect to Z. Why? Because Z hat times Z hat is just 1. So we are left with this one. And this is just equal to 1. So therefore the divergence of this vector having this form is equal to 1. So can siya this another entity from divergence to curl. So for the curl, the definition is given by equation 18. So this is just traditional method is the what we call the basket method. Okay. So del cross V. So we have x, y, z unit vectors, and then we have the definition of our del. We have partial of x, partial of y, partial of z, then vx by y, vz. So one way to do this, we have this traditional process. So for x hat, actually nana siya hat because it's a unit vector. So nana siya hat, right? Hat. So for x, imo siyang kabiran diha, right? Wala na siya sa x. And then you multiply this one. So we have partial of z, partial y, tama? Minus this one, partial of vy, partial z. Okay. Then plus, so imo na siyang i-erase diha. But this time, opposite na siya. Instead na mag-start ka dinhi. Right? Kaya ang convention ana usually is minus man na siya. But for if butang nimo siya og plus, then you do this. You start with this. So we have partial of vx, partial z, and then we have this. Partial v, sayo. This is partial, tama. This one. Partial vz, partial x. Okay. For the z hat, so wala na siya. Then you cross multiply. Partial vy, partial x. You have this partial vy, partial x, and then we have partial vx, partial y. So we have this definition of a cross product or curl. So notice nga ang iyang output niya is also a vector. So we have the curl of a vector is also another vector. So it's a vector niya, vector form. So notice that the curl of a vector function is like any cross product, a vector. So you cannot have the curl of a scalar. Again, that's meaningless. So we have one example for the curl. So let's take a look at this example. This one is from our reference, from my lecture notes that I uploaded. So pwede nyo siya matanaw dito. So we have these two vectors here, and we want to find the curl of the following two vectors. We have the VA and then the VB. So this is the vector A and this is the vector B. Okay, for letter A, we will get the curl. So the formula is just this one, cross VA. So employing the basket method that I introduced a while ago, we have x hat, y hat, and the z hat. Then this is partial x, partial y, partial z. And then for the VA, it has the following component. You have the x and y component. So this is negative y, and then this is x, and it has no zero. It has zero component on the z. Okay, so we get here x hat. So x hat, so tabunan ni siya. Then we cross multiply. So this is 0 minus. So we have partial x, partial z, and then plus y hat. So sa y hat, instead na magsugod ta ani dinhi, duta sa opposite. Okay, sugod ta diri. So we have negative partial y, partial z, minus 0, right? This is 0. Okay. Plus the z hat. So cover na siya. So we have partial x, minus. So minus po ni siya. This becomes plus. So partial y. So our answer becomes, so for the x hat we have, so partial of x with respect to z, this is just 0, so 0 is here. How about this? This is just 0 gihapon. And for the z component, so we have partial x, we have 1, partial y, we have 1 also, so 1 plus 1 we have 2. So this is 2z hat. Okay. How about for letter B? So the same gihapon ang ato ang buhaton. We have del cross VB. Then we have x hat, partial x, partial y, partial z. Then we have 0 for the x component, and then we have x for the y component, and 0 for the z. Okay, so for the x hat, so wala na siya x hat, so we have 0 minus partial x, partial z, right? Plus y hat. So for the y hat, we have, this is 0 minus 0 gihapon. Okay, plus the z hat. So z hat, we have partial x, minus 0. Right? So simplifying, so we have here partial x, partial z is 0. So 0 ni siya. 0. This is also 0, right? And this is 1. Partial x, right? This is z, partial x. Okay. This is 1. So we get actually z hat. So That's it.